So, what's really going on inside the mind of an AI? You know, these systems are making more and more critical decisions about our lives, but a lot of the time, even the people who built them can't fully explain how they get to an answer. Today, we're going to crack open that mystery and see what's really inside. Just imagine this for a second. You apply for a loan, maybe a job, or even get into university, and you get an automated rejection. The very first question you're going to ask is, why? But what if the answer is locked away inside a system that's so complex, nobody can give you a straight answer? That's the kind of high-stakes problem we're diving into. And that right there, that brings us to what experts call the black box problem. It's really the central challenge in making AI something we can trust and, make fair. We're using these incredibly powerful models, but that power often comes at the cost of transparency. So, what exactly is a black box? Well, it's an AI where you can see the inputs, like all your application data, and you can see the output, a simple yes or no. But the logic in between? It's a complete mystery. And this is a massive issue in really critical fields like finance and healthcare, where just one unexplainable decision can have totally life-altering consequences. So, how do we solve this? Well, the field has pretty much developed two very different approaches. You can think of it as a fundamental choice. Do we build a system that's simple and clear from the very start, or do we build a super powerful, complex system and then invent ways to interrogate it later? So on one hand, you've got interpretability. This is the idea of building a transparent glass box model where the rules are clear right from the get-go. And on the other hand, there's explainability, where you take that complex black box and basically act like a detective using special tools to figure out why it made one specific decision. Let's take a quick look at some of these glass box models. You've got your classics, right? Things like linear regression, which is perfectly clear. Every single factor in your application just gets a specific weight. Then you have decision trees, which are just a series of if-then rules that anyone can follow. The slide also mentions GAMs, which are cool because they can capture more complex relationships, like a situation where doubling your income doesn't exactly double your chances of approval. Now, while these models are wonderfully transparent, there's a catch. They often struggle with the messy, complex patterns of the real world, which can make them less accurate. Okay, so if the simple models just aren't powerful enough, we're right back to that black box. The question is, how do we interrogate it? All right, let's open up the toolkit that data scientists use to get some answers. One of the most intuitive tools out there is called LIME, and the idea is just brilliant. To explain one super complex decision, LIME builds a tiny, simple model that's only valid for that one specific case. It's kind of like creating a simple blueprint to explain just one corner of a massive, complicated building. But, LIME isn't perfect. Its explanations can be unstable, you might get a slightly different answer every time you ask. It also kind of assumes the model is behaving in a simple, straight line right around your specific data point, which often isn't the case. And that instability, that's what really pushed researchers to find something, well, a bit more robust. And that brings us to shapely values. Now, this idea actually comes from game theory, and it is all about fairness. Imagine your application's features, your income, your credit history, are all players on a team. Shapely values figure out exactly how much credit each player, each feature, deserves for the team's final score, or in our case, the model's final prediction. So how does it work conceptually? Well, it starts with a baseline prediction. Then it starts adding features one by one, in every possible order you can imagine, and it measures how much each feature changes the prediction when it joins the team. By averaging all those contributions out, you get a really fair and solid measure of each feature's true impact. And here's what that looks like in practice. For a loan denial, the model might start with some base probability. Then it adds the impact of your specific features. A history of delinquency, that might add a lot of risk, but a high income could reduce it. When you add them all up, you get the final prediction. All of a sudden, that black box decision is broken down into pieces we can actually understand. Explaining one single decision is great, but sometimes you need to understand the model's overall strategy. We need to zoom out from the individual trees to see the entire forest, So this brings up a really crucial point, the difference between local and global explanations. Local tools, like the ones we just talked about, they answer the question, why was this loan denied? But global tools look at the bigger picture. They answer questions like, in general, how does this model treat income? You absolutely need both to get the full story. So one popular global tool is the partial dependence plot, or PDP. It shows you the average trend. For example, a PDP could show that, on average, the risk of a loan default goes up as income goes down. But that phrase, on average, well, it can be a very dangerous phrase. Because the average can totally hide what's really going on. And that's where ICE plots come in. Instead of one single average line, ICE draws a line for every single person in your data. And suddenly, you might see that while the average trend holds for most people, for some specific group, the story is completely different. It reveals all the hidden complexities that the average just smooths right over. But maybe the most powerful type of explanation is a counterfactual. It doesn't just tell you why you were rejected. It tells you the smallest change you could make to get approved. It's direct, it's personal, and most importantly, it's actionable. Now, all these technical tools aren't just for curious data scientists. They are becoming absolutely central to law and regulation as society really starts to grapple with the impact of all these automated decisions.
And this isn't just theory, it's literally becoming law. Regulations like Europe's GDPR have established a right to explanation. The new EU AI Act goes even further, mandating clear explanations for any high-risk AI system, the very systems making decisions about our jobs, our finances, and even our freedom. Explainability is no longer a nice-to-have. It's a legal requirement.
This forces everyone to confront the fundamental trade-off head-on. Do you choose a simpler, more transparent model that might not be quite as accurate, or do you go for the cutting-edge, high-accuracy black box and then do the hard work of explaining it? There's no easy answer here, and the right choice really depends on the stakes. For a movie recommender, accuracy is king. For a medical diagnosis, you need both accuracy and the trust that comes from a clear explanation. One really practical solution that's gaining a lot of ground is the model card. And honestly, the best way to think of it is like a nutrition label for an AI. It's a standard document that clearly states what the model does, how well it performs, where it's likely to fail, and what biases it might have. It's a huge step toward real-world transparency. Which leaves us with a final, really critical question. As these systems get more and more woven into our lives, we have to decide what level of clarity we demand. So when an AI is making a call on your future, what kind of explanation do you believe you truly deserve?